Hello and welcome to this presentation related to integration applications. In a previous presentation we considered the applications of finding areas under curves and finding volumes of revolution. In this particular presentation we're going to calculate the mean and the root mean square r.m.s values for periodic waveforms. The formulae we'll be using are shown here for the mean value, which will involve the integration process, and calculating the r.m.s value, again involving use of integration. It is assumed you've seen the previous presentations related to introduction to integration and calculating the areas of volumes and revolutions before reviewing this presentation. Here's a brief presentation overview. Presentation commenced with an introduction to this particular topic area, then a recap of standard integrals, showing our integral tables, and also a recap of trigonometric identities, some of which we'll be referring to within certain solutions. And next we have formulae for calculating the mean and the r.m.s values of particular waveforms. Then we have example 1r. We're given a waveform. We have to calculate the mean and the r.m.s values. And here are the approximate start times related to the various sections stated on this slide, hopefully to aid your ease of access through the presentation, but please note these times are rounded to the nearest minute. Presentation overview continued. We then have some tutorial questions 1R, 2R and 3R, for you to attempt at your own pace, although full work solutions are provided. And here are the approximate start times if you want to skip directly to the solutions to question 1R, question 2R, question 3R. But please note again these times are rounded to the nearest minute. Just a brief note here, this channel is essentially dedicated to mechanical science and mechanical engineering, but calculating the mean and r.m.s values is often associated with electrical engineering, which is not my field of expertise. So here's just a brief overview of where the mean and r.m.s values are used within electrical engineering. Within alternating current work, the mean value is often calculated, formula for calculating the mean value shown here, 1 upon b minus a constant multiplied by the integral of y dx between the limits of a and b, but is not of such great significance because electrical engineers are usually interested in calculating the power produced, which depends on the square of the current or the voltage values. So in such cases, the root mean square, r.m.s for short, is determined. Here's the formula for the root mean square. It's the square root of 1 upon b minus a, constant, multiplied by the integral of y squared dx between the limits of a and b. So that's just a backdrop given the context of the mean value and root mean square value formulae. Here's some reference information extracted from our previous presentation related to standard integration and use of standard forms. This is table 1 from the previous presentation. On the left hand side of the table here we have the integrand. That's the various functions of x's shown here that have been integrated, ax to the n, sine ax, cos ax, etc. Here's what's termed the integral. Once we've integrated the function of x, these are the solutions. Notice the constant of integration is shown here in each of the integrals. Remember from our previous presentation, we only need to state the plus c if we are solving an indefinite integral. Also on the right hand side, I've included the laws and the rules of indices. We've used these many times now, but sometimes they can be used to help simplify the integrand and place it into standard form. We will refer to trigonometric identities. That's something we reviewed again in a previous presentation. This slide shows the many types of trigonometric functions and identities. In our previous presentation we referred to Pythagorean identities, shown highlighted here. But within this presentation you'll see in some solutions we'll need to use what's referred to as the half-angle formulae to help us make the integrand into standard form for the integration process. And this is the particular formula or identity we'll be using within some of these solutions. This slide just shows the trigonometric identities more clearly. What we will find within some of these solutions is that the equations we will need to integrate will involve the sine squared x function, and that's not a standard form in our tables. Back to this table here, there's no integrand for sine squared x. So what you'll see is we'll replace the sine squared x function with this expression. That is a half multiplied by the bracket of 1 minus cos 2x, which when expanded will leave us with standard form. Here's the cos ax integrand. We also have the identity for the cos squared x function, again allowing us to move from a non-standard integral to an integral in standard form. So let's consider briefly again the formulae for the mean value of our particular periodic waveform. This is calculated from the formula 1 upon b minus a. B and a shown here as the limits of the integral, and that constant is multiplied by the integral of y dx, and y dx is the area of this elemental strip, height y multiplied by width dx, and of course we're integrating between the limits of a and b shown here. So that's calculation of the mean value. To calculate the r.m.s value, our formula is the square root of, again here 1 divided by b minus a, but this time the integral is of y squared dx between the limits of a and b. Just note for reference, these continuous waveforms are often plotted y against omega t. So instead of stating y is equal to a function of x, we state y is equal to a function of omega t. So often we're not integrating with respect to x, but we're integrating with respect to omega t. So in this context, we replace dx with d omega t. We'll illustrate this through an example on the following slides. So example 1r, a sinusoidal voltage is given as V is equal to 100 multiplied by sine omega t volts. I just note, as stated on the previous slide, we can read the 100 sine omega t as effectively 100 sine x. So instead of integrating in respect to x, we're integrating in respect to omega t in this particular example. We'll show that below. Using integration, we've got to determine over half a cycle, A, the mean value, and B, the r.m.s value. So here's our solution for part A, the mean value. Here's the mean value formula from our previous slide, 1 upon b minus a, the integral of y dx between the limits of a and b. Inserting the values, that's 1 divided by, notice b is going to be pi here because it's half the cycle we're considering. The full cycle for the sinusoidal waveform would be between 0 and 2 pi radians, but for half the cycle, that between 0 and pi radians. So here's our y function, and that's multiplied by d omega t. In other words, we're integrating with respect to omega t in this case. Just note here that the value of 100 is being brought outside of the integral sign, and that's divided by pi minus 0, of course that's pi. So now we're ready to integrate sine omega t with respect to omega t between our limits of 0 and pi. Sine omega t is a standard form. So again, just for reference, this sine omega t is integrated with respect to omega t. So think of that as sine x integrated with respect to x. So from our standard tables, integrating sine x, we're integrating sine x, a is effectively 1 here, and that integrates to negative cos 1x upon 1. So in other words, sine x integrated with respect to x is negative cos x. So sine omega t integrated with respect to omega t becomes negative cos omega t. The constant 100 divided by pi remains outside of the bracket, but because now we've integrated, we move to square brackets, and our lower limit of 0, upper limit of pi stated at the rear of the square bracket. On this next line here, to simplify the calculations, the negative has been taken outside of the square bracket, and now I simply insert my upper limit of pi, my lower limit of 0. Evaluating, the cos of pi is -1 and the cos of 0 is +1. Thus, evaluating the square bracket, we have -2, that's multiplied by -100 outside of the bracket. Two negatives here make the positive, so we end up with +200 divided by pi, and I've written that as pi to -1, and that's volts. And that's approximately equal to 63.66 volts to 2 decimal places. So there's the mean value of the waveform calculated for the half of a cycle for example 1r. Example 1r solution continued. Now we're going to calculate part B of example 1r, and that's the r.m.s value. Here's our formula for the r.m.s value. Again, our b is pi and our a is 0 for this particular example. 1 upon pi minus 0, so limits. But notice now we have the 100 sine omega t squared integrated with respect to omega t. Here's our limits of the integral, 0 to pi. And of course we have to square root the answer in this particular case. Notice the 100 is squared under the square root sign, but if we then square 100 and take it outside of the square root sign, it becomes 100 again. So that's why the 100 is shown here outside of the square root sign. And we're left inside the square root 1 upon pi multiplied by sine squared omega t integrated with respect to omega t between our limits. Now, as mentioned previously, as our standard tables, there's no sine squared function here. We have a sine function, sine ax, but no sine squared function. So we're considering this is not standard form. So we're going to use our trig identity, noting that we can write sine squared x in terms of a half 1 minus cos 2x. In this instance, I've just shown this rearranged from this form, simply because in some textbooks the identity is shown as cos 2x equals to 1 minus 2 sine squared x. But we need it in the form of sine squared x equals to a half in the bracket 1 minus cos 2x. So note in this next step here, calculating r.m.s value, we have 100 outside of the square root sign still, and 1 upon pi multiplied by integral of, and notice this sine squared omega t term here is now replaced with the half multiplied by 1 minus cos 2 omega t in the bracket. So notice the x is equal to omega t. This x here in our trig identity is the omega t shown here, which then we need to multiply by 2, shown here. We can then also bring the half outside of the integral, shown here. So we're now integrating the 1 minus cos 2 omega t with respect to omega t between our limits of 0 and pi. So integrating constant 1 with respect to omega t, that becomes omega t. That's like integrating 1 with respect to x, that becomes x. And integrating negative cos 2 omega t with respect to omega t, that becomes negative sine 2 omega t divided by 2. So again, thinking cos ax integrated with respect to x becomes sine ax divided by a. So we have in this case cos a omega t, where the a is 2. So that becomes sine a omega t divided by the a. So again, trying to think of this as cos ax integrated with respect to x. This is cos 2 omega t integrated with respect to omega t. So the a is 2 and the x is omega t. Hopefully that helps you follow the pattern through in our standard tables. I would encourage you to start the presentation, just think through how we've integrated from the minus cos 2 omega t with respect to omega t. It's all related to the standard form. Of course, as always, we state the lower and upper limit at the end of the square bracket here. On the next step, I simply impose the limits. So the upper limit of pi, substituted for omega t, here and here. Then I insert my lower limit for omega t, which is 0 in this case. Evaluating this first bracket here, I have pi minus 0. Note the sine of 2 pi is 0, sine of 360 degrees. And from the second bracket here, I have 0 minus, and sine of 0 is 0. So my final answer for r.m.s is 100 multiplied by the square root of 1 upon 2. Notice how this pi cancels with this pi to leave with the half, 1 upon 2. Of course, that's the unit of the volt. And that's approximately equal to 70.71 volts to 2 decimal places. So again, I'd encourage you to start the presentation and think through for part B of example 1R. Quite a complicated solution, and although ultimately using standard forms, the use of these standard forms needs to be thought through quite carefully because of the notation used. But hopefully that's given you an insight into how to calculate r.m.s values for a given waveform. Here's some tutorial questions we were given related to calculating the mean and r.m.s values. I'll let you read these questions at your own pace, although I will briefly overview the full work solutions on the following slides. In question 1R, given a waveform for a current, we're asked to evaluate the mean and r.m.s values. Notice the range here is given as t is equal to 0, t is equal to 10 milliseconds. So we're integrating here with respect to t and not omega t. So that actually simplifies slightly the use of the standard forms. Answer is shown in the bracket. Question 2R. We're given that the vertical height h, kilometers of a missile, varies with the horizontal distance, labelled as d here in kilometers. And we're given a relationship between h and d. So we've got to calculate the mean height, given the limits of d to be 0 and 4 kilometers. So no r.m.s value calculated here. Answer shown in the bracket. And finally, question 3R. We're essentially given an equation, y is equal to x plus x to the negative 1. And we've got to calculate the mean. And what they term as standard deviation here, in this particular case, that's actually the r.m.s value. And we're again given the range of x from 1 to 2. Answer shown in the bracket. I'd encourage you to start the presentation and attempt questions 1R through to 3R, but I will very briefly outline the full work solutions on the following slides. Here's question 1R, commencement of the solution. Initially calculating the mean value. Just notice here we're actually integrating with respect to t, not omega t. And we're given the equation for I, shown here inside our integral. And we have our limits here of t and 10 milliseconds. And note the value of b here is 0.01 seconds. This is now a standard form. It's taken a 25 outside of the integral sign here, and also the 0.01 outside of the integral sign. So inside the integral standard form, it's sine 100 pi t. Read that as sine of at, where a is 100 pi. So when we integrate sine at respect to t, we end up with negative cos at over a. That's essentially what we have here, negative cos 100 pi t divided by 100 pi. Note for your reference that the sine of 100 pi t is in the form of sine at, so a is the 100 pi here, and we're integrating with respect to t. So integrating sine at becomes negative cos at upon a. That's our standard form in this table. But of course the a in this problem is 100 pi, so that's why the 100 pi occurs in the denominator when we integrate. So here's the a shown here. Just note for reference here, the 25 divided by 0.01 is of course the same as 2,500. And of course the limits of the integration process stated at the back of the bracket. On the next step here, we simply divided the 2,500 by the 100 to leave us with negative 25 outside the bracket, and of course the pi in the denominator has been taken again outside of the square bracket. All we do now is impose the limits, the upper limit 0.01 here, the lower limit of 0 here. Now evaluating 100 pi multiplied by 0.01 becomes cos of pi, and we subtract from that the cos of 0 for the lower limit. Referring to the cosine waveform, cos of pi is -1, cos of 0 is +1, and as we're subtracting the values, the bracket becomes -2. Multiply that by -25, we end up with +50, still divided by the pi, of course. So 50 divided by pi milliamps is the mean value, which can be stated as 15.92 milliamps to 2 decimal places. Question 1r, solution continued. Let's now consider the r.m.s value calculation. Formula for r.m.s shown here. Remember, in the formula we have the function squared. This is the I function shown here. And of course it's squared. I is integrated with respect to t because it's a function of t. Our limits here, t is equal to 0 to t is equal to 10 milliseconds. So a in this case is 0 and b is 0.01, 10 milliseconds. So here's our equation for I, 25 multiplied by the sine of 100 pi t. It's all squared, integrated with respect to t. Here again are the limits on the integral. The next step on the right hand side is 25 has been taken outside of the square root. Notice it's 25 squared, but then we're taking 25 squared outside of the square root, so that becomes 25. So here's 25 squared, all square rooted, is of course 25, shown here. And of course, taking the 0.01 outside of the square root 0.01, we have 0.1. Calculation shown here. And of course, the final step on the slide is simply 25 divided by 0.1. That's like multiplying 25 by 10. So 250 now outside of the square root sign. So now we're ready to undertake our integration process of our sine squared 100 pi t function. Question 1r, solution continued. Just repeated this line from the previous slide. So now we need to integrate this function, sine squared 100 pi t, with respect to t. Again, we know that's not a standard form in our table. No sine squared t in the integrand column here. So we're now going to convert the sine squared 100 pi t using our trig ID. So again, from our previous slides, we know that sine squared x is equal to a half multiplied by in the bracket 1 minus cos 2x. So noting that x is equal to 100 pi t in this case, we now have a sine squared of 100 pi t on the left hand side is equal to the half 1 minus the cos of twice the x, so 2 times 100, that's 200 pi t. So this is now the function we will integrate on the next slide. Question 1r, solution continued. Repeated our trigonometric identity from the previous slide. So using this trig identity, we replace the sine squared 100 pi t with this expression here. Just notice the next step, I've taken the 2 outside of the square root sign shown here. If it helps with your understanding of the fractions, think of this as being 250 divided by 1, then taking the 2 outside, and becomes 250 divided by the square root of 2, shown here. That now leaves me with the integral in standard form here of 1 minus cos of 200 pi t. On the next line, I've just divided the 250 by the square root of 2 to show the answer in 3 decimal places. I could have left it as 250 divided by the square root of 2 though. And integrating negative cos 200 pi t with respect to t, I get negative sine 200 pi t divided by 200 pi. Our standard forms, when you're integrating cos ax, becomes sine ax upon a. In this case, the a is 200 pi and the x is t. That's how we end up dividing by 200 pi, shown here. Notice the limits on the back of the square bracket as usual, and the square bracket is under the square root sign, of course, here. So imposing the upper limit into the first bracket here, and the lower limit into the second bracket. Notice all terms are 0 in the second bracket because t is 0. The sine of 0 is 0. Notice this term will also be 0 if the sine of 200 pi times 0.01 is also 0. So finally, evaluating the r.m.s value is 17.68 milliamps to 2 decimal places. Question 2r, here's the solution. This question we have to calculate the mean height for a missile, and we're given an expression between the vertical height h and the horizontal distance lowercase d here. We have to integrate between d is equal to 0 and d is equal to 4 kilometers. So our mean value formula here, generically given, is 1 upon b minus a. We integrate y with respect to x between the limits of a and b. So in this case, the y is actually h and the x is d. So it becomes 1 upon the a limit is 0 and the b limit is 4. And we're integrating the h function, which is 4d minus d squared, with respect to d. Just note the notation used. Integral limits 0 and 4. This is all standard form. Integration 4d integrated with respect to d becomes 4d squared upon 2, and negative d squared integrated with respect to d becomes negative d cubed upon 3. We have 1 upon 4 outside the square bracket and limits of 0 and 4 here. What has happened in the next step is this term has been simplified. 4 divided by 2 is 2, so 2d squared here. Then we insert the upper limit of 4, and of course inserting a lower limit of 0 for d, all the terms become 0. And evaluating the mean value, the mean height in this case, is 2 2/3 or 2.667 volts to 4 significant figures. Just note for reference, the unit should not be the volt, but the kilometre. I'll let you work through the arithmetic at your own pace. And finally, question 3r solution. This particular question, we're given a function, y is equal to x plus x and negative 1. And we have to calculate the mean and the standard deviation, which is actually the r.m.s value, for limits of x between 1 and 2. I'll let you review the solution at your own pace. Just note that obviously x and x and negative 1 or 1 upon x are standard forms in our table. And the mean value is 2.197 kilometers to 4 significant figures. And question 3r solution continued. Here's the calculation for the r.m.s value using our standard formula shown here. And I'll let you review this at your own pace. Don't forget, of course, that we have to square the y function here that states in the formula. So this is the y function squared, and that's what we have to integrate. And for your reference, I've tried to illustrate the bracket expansion from here in great detail to show how we've derived the final simplified expression shown here. Note that I expanded the binomial brackets using what's called the crab-claw method. We've reviewed this in a previous presentation. And again, evaluating the r.m.s value, 2.198 kilometers for significant figures. Here's the bibliography used to help generate the presentation. Very good technician engineering maths book here. And I hope this presentation has been of use to you, and as always, thank you for viewing.